Good evening everyone. I am Trinath. My roll number is 19BQ180426. Today I want to discuss about a few topics in vlsi. Some of them are comparison between CMOS and bipolar techniques and stick diagrams of NMOS and PMOS. Let us coming to CMOS and comparison between CMOS and bipolar technologies. They are first one is in CMOS power dissipation is very low. In bipolar technologies, power dissipation is very high. In CMOS technologies, input impedance is high, but in bipolar technologies, input impedance is low. In CMOS technologies, we have high margin, but in bipolar technologies, we have low voltage swing logic. In a CMOS technologies, we have high packaging density, and in bipolar technologies, we have low packaging density. In CMOS, we have sensitive load is very high, and in a bipolar, sensitive load delay is very low. In a CMOS, output drive current is very low, but in a bipolar, output current is very high. We know that in CMOS we have high transconductance, we have low transconductance, and in bipolar we have high transconductance. CMOS having a bipolar bidirectional capability, but bipolar does not having a bidirectional capability. CMOS having a near ideal switching device, and in bipolar technologies it is known as essential unidirectional. These are some of the MOS layers. If the lines in the metal is in this direction, it is known as polysilicon. If second one is a symbol of SiO2. And if the difference between the lines is very, if the space between the lines is very small, then it is known as n-type diffusion. If the space between the lines is very large, then it is known as p-type diffusion. These are the symbols to indicate n-type diffusion and both the p-type diffusion. Next one, metal 1, metal 2 are the symbols of metals. Depletion region, this is known as the depletion region symbol, and we know that implanted channel in the depletion mode NMOS transistor symbol is like with indicated with the dotted lines. Next one, coming to stick diagrams. Stick diagram is nothing but it is a circuit consisting of sticks. Stick diagram gives the information about the layers of a circuit with color coding. It is used to represent all the each and every layer is represented with a color. In NMOS transistor, n-type diffusion is indicated with a green color. In in NMOS transistor, polysilicon is indicated with a red color. Metals are usually indicated with a blue color. And the implant is nothing but indicated with a yellow color. That is nothing but in depletion is indicated with it is yellow color. Contact cut is nothing but is indicated with a black. Buried contact is indicated with a brown. PMOS transistor. PMOS transistor is nothing but in PMOS it is nothing but p-type diffusion is indicated with yellow color. Polysilicon with a red color, and metals same as in NMOS transistor, they are indicated with a blue. Implant also same as in NMOS transistor, it is indicated with contact cut is indicated with a black. Buried contact is indicated with a brown. For NMOS transistor, it is AND gate is indicated with a series, OR gate is indicated with a parallel. In PMOS, AND gate is indicated with a parallel, and OR gate is indicated with series. Let us see some more examples on NMOS n-type diffusion and p-type diffusion. Let us consider the inverter in n-type diffusion. First of all, we have to draw metal lines. You know that I already mentioned that metal lines are indicated with sky blue color. Let us mention this upper metal layer as VDD and the lower metal layer as VSS. Let us consider a diffusion layer of n-type. N-type layer is indicated already we mentioned that in the previous slide. It is indicated with a green color. Then we know that the contact cuts color is black, and we mention it the contact cuts with black color. Then after mentioning the diffusion layer and metal and contact cuts, then we have to take the polysilicon and implant with this depletion layer. We know that the polysilicon color is indicated with the yellow. Inverter is nothing. For inverter, we know that the given input is opposite of the output. That is, if we give 1, then the output is 0. If we give 0, then the output is 1. So to implement this circuit, we have a CMOS design like we have a CMOS design like this, as mentioned in the given slide. Then we indicated with the we indicated the polysilicon with red colors, and we for output we have to extend the polysilicon line to draw the output for NAND gate. We know that NAND gate is the opposite of AND gate, and it is nothing but if any of the input is if both the inputs are not 1, then the output is 0. Some of it is AND gate is nothing but the opposite of AND gate. That is, if both inputs are 1, then the output is 0. Otherwise, then the output is 1. To implement this circuit, the CMOS circuit will be developed like this. As we mentioned in the previous slides, for in n-type diffusion for AND gate, the gates are to be in series. So we mentioned A and B is in we mentioned the gates of A and B are in series, and then we connect them to the NMOS transistor, and then we drag the output. This is the diagram of an AND gate. Next, AND gate. We know that for AND gate, if both the inputs are 1, then the output is 1. If the any of the input is not equal to 1, that is, if both the inputs are 0, then the output is 0. If the input if one input is 1, another input is 0, then the output is also 0. If one input first input is 0 and second input is 1, then the output is 0. In an AND gate, it is the output is high only when the both inputs are high. To implement this, we have to connect a NAND gate with a NOT gate. Already we seen in previous slide, this is an AND gate CMOS logic, and this is the NOT gate CMOS logic. If here to implement AND gate, we just connect the inverter gate at the output of the NAND gate. Here the diagram will be shown like this. Just we in the NAND gate stick diagram output polysilicon line, we connected the NOT gate, then it becomes AND gate. For NOT gate, we know that it is a complement of OR gate. For OR gate, if any of the input is 1, then output is 0. If both the inputs are 0, then the output only 0. That is nothing but if both the inputs are 0, then the output is 0. If one input is 1 and another input is 0, then the output is 0. If one input is if both the inputs are 1 also, then the output is 1. NOR gate is nothing but the complement of OR gate. That is nothing but if both the inputs are 0, then the output is 1. Otherwise, then the output is 0. To implement the NOR gate, we know that as in mentioned, for OR gate we have to mention the two inputs in parallel. That's why here A and B are in parallel. In the bottom of the slide, we see the diagram of NOR gate. To implement this, first we have to mention two metal layers, and then we have to mention the diffusion layer, and then we mention the polysilicon layer, and at the output we draw the extension to the polysilicon line. Coming to the P diffusion layer, it is nothing but it is similar to NMOS, but in place of green color we take yellow color. Remaining part is same. But one more thing is also here change. For AND gate, the gate should be in parallel. For OR gates, the gate should be in series. Coming to inverter, we know that inverter is a complement of the given input. That is, if we give 1, then the output is 0, otherwise it is 0. Similarly, we in n-type diffusion, we mention the polysilicon layer in below, and the output in a pull-up element, and the input is pull-down element. Here the elements are reversed. Here the input is at pull-up place, and the output is drawn at the pull-down place. For implementing the NOR gate is nothing but a complement of OR gate. We know that for OR gate, the gates should be in series in this diffusion. So we make A and B is in series. Then we have to draw the metal lines, and then we have to draw the diffusion layer, which is indicated with yellow color, and then we place the polysilicon elements on the diffusion layer. Then we drag the output at the diffusion layer. Coming to NAND gate. NAND gate is nothing but the component of AND gate. That is, if both the inputs are 1, then the output of the NAND gate is 0, otherwise the output is 1. Coming to implementation of NAND gate, is nothing but we mentioned that in a p-type diffusion, for AND gate, the gates should be in parallel. So we mentioned that the A and B are in parallel. Then we drag the output, then the output is in NAND gate. Here A and B are in parallel. First they take the metal layers and then the diffusion layer, then place A and B are in parallel, and then we drag the output. Then we get the output. Coming to A plus, let us see some more examples on p-type diffusion. Nothing but A plus C and A plus C into B plus C whole complement. These are the implementation. For A plus C, it is in p-type, so it is OR gate, so we can set the gates are in a series. Then to get the OR gate, we have to complement the NOR gate. Then we can connect the inverter at the output of the A plus C NOR gate. Similarly, for A plus C into B plus C, these are in AND gate. So we under inverter, first we have to connect A plus C. These are in OR formation, so we have to make in them in series. B and D are in also series. For AND gate, they should be parallel. Then we connect the parallel and we can draw the output. Thank you.